Okay, so we are finally in the position to talk more about what we actually wanted to talk about in the whole summer term. So we have now introduced a wealth of theory or theoretical aspects that we all need in the following for the rest of the course. But we went through a little bit of a digress or detour, and now finally can actually have the language and have the concepts to address what we actually wanted to address. And what we actually wanted to address was, of course, random field-based p-value correction. And the original idea that I introduced was that what we want to do is to come up with a null model, so a null hypothesis or a null model better, that we can use to assess our observations of blobs or activity clusters in fMRI. And we did that in the very beginning, so I showed you how that looks in SPM, and then I made a little drawing of how you can imagine that with the voxels. And then we went through quite some stuff, but never really returned to the question of now I'm talking about this null model, but today we finally will. So remember again that the null model and the whole concept works as follows. So in 1D, so you have to make the transition to 3D in your head essentially. So the x-axis here in this plot now should be space, and the y-axis should be something like a test statistic or effect value, whatever. And what we are trying to do all the time is to come up with a probabilistic model that generates these distributions over space, and we call them a random field and random field realizations. And what we want to use the whole thing for is to compare these realizations, so the theory of these realizations, with the values that we that we actually observed. So, for example, if we have voxels, then what we may have observed something like this in discrete space. We have these values here observed, and to do that from the perspective of classical statistics, what we need to be able to talk about is the probabilities or the expectations of features of these random fields under the hypothesis that there is no effect, right? So this is classical frequency statistic, like in the T distribution. You say, if there is no effect at all, then I expect this distribution of T values. Now I have observed a T value of, let's say, 3. Then under the null hypothesis, I know that a T value of 3 or larger than 3 is fairly unlikely. So I might want to reject the null hypothesis. So this is the logic of null hypothesis testing, and this is, of course, the same logic here. Now, we are almost there. My voice is still a little bit sore. Those Guns N' Roses yesterday in the Olympia Stadium. I might have lost a little bit of voice there. It's still better than Axel's voice these days. Anyway, now we can talk about probabilistic features of these random fields, and that's what we want to do. And what we specifically want to focus on are excursion sets. So we also talked about excursion sets. Maybe let's put in one more realization here so that there's a little bit more to see. So another realization. We talked about forming excursion sets, and these excursion sets were introduced by introducing threshold value U, which is called the cluster forming threshold in fMRI. And then the excursion sets were those parts of the support space of the random field for which the probability, for which the values, not the probability, for which the values are larger than this threshold level U. Yeah, so in this case, this would fall, this region here is corresponding to this in space, would be part of the excursion set for this level U. This would be part of the excursion set. So this and this. And of course, the excursion set depends on the threshold level as much as it does depend on the random field. Yeah? So if you increase the threshold level, in the end, only one thing would survive. Good, we've seen all of that. Now, so in the end, what we want to do is that we have our observed voxel values here. And we want to say something like in the t-distribution, like observing such a voxel t value, for example, under the null hypothesis has this and this probability. Or observing next to each other a couple of voxels of this height here has that and that probability. Yeah, so that's what we want. And from the theory of random fields and what we've seen so far, we can now basically introduce a certain set of excursion set features. So we will always talk about the excursion set. Then if we have our real observation and we form an excursion set based on a given threshold value, we can say something about their probability. So to make this more concrete, think of the excursion set as this set which depends on some level U. And the important step, of course, that I didn't mention is that the excursion set itself is, of course, a random entity. Yeah. So if you fix the threshold level and obtain another realization, for example, of this orange random field, which might look like this, the excursion set is different. Yeah, so the excursion set itself is a random entity, and it has certain features that we want to talk about that are then also random entities. So, what are the features that I mean by excursion set features, and what kind of probabilistic aspects do we want to look at? These are the following, and that's basically the program for the next, I guess, 2 sessions. The first thing that we want to investigate or talk about is the expected volume. The expected volume of the excursion set. Let's do it like this, the expected volume. So what does that mean? That means if you look at this excursion set here, where we have these 3 intervals that make up the excursion set, then the question is, what is the volume of those? So essentially the Lebesgue measure or some other volume measure. It will actually be Lebesgue or Riesel volume. But the question is, how big is the excursion set at a given threshold level under the assumption that there is no effect. Yeah, and then so if you always have to think about also brain imaging in the back of your head. So if you threshold a brain imaging map with some T maps at a certain level, how many active voxels, if you want, do you expect just by chance? Yeah, just under the null hypothesis of no effect. And then, of course, if you know these theoretical features under the null hypothesis and you have something on your computer screen in SPM, then you can say, oh, actually, these are as many voxels as I actually expect under the null hypothesis. So maybe this is not an effect, but it's pure noise. or you have many more, and then you say, oh, maybe this means some activation, so maybe I have something significant. So that's the first thing that we need to talk about. Then we will talk about the expected number of local maxima So here, for example, for this orange thing, you see that there are 3 local maxima. So there's one, there's another one, and there's the third one over this space. So these, and we will investigate it in more detail, but yeah, very roughly, the number of local maxima refers to the number of peaks, or definitely like that, or the number of blobs, if you want. And then again, at a given threshold value that you threshold your statistical parametric map at, the question is how many of these local maxima do you expect? And again, if there are more than you expect under the null hypothesis, then you are surprised and say, okay, that might mean something. If there are as many as you would expect under the null hypothesis, you say, okay, that's not too surprising. So that's the expected number of local maxima, and a very closely related entity, specifically from the brain imaging viewpoint, is the expected number of clusters. Where clusters are, at least for the moment, until we go into how SPM evaluates clusters, just as understood in this informal setting of that things cluster together. Yeah. So of course, local maxima and clusters in excursion sets are not necessarily the same. We will see that in more detail. But roughly, if you have a local maximum here, then you also, of course, have a cluster around here. So that's what we want to talk about. And then finally, we need to talk about the expected volume of a cluster. So this essentially, from a brain imaging perspective, refers to the question of how big a blob is. Yeah. So maybe do that again from the brain imaging perspective. What we are talking about here is if you have this T-map and then you use a threshold value and obtain a network of activations, as we like to say, although these are really just excursion sets, then the question is, what's the overall volume of this under the null hypothesis? How many clusters or local maxima do we have? So that also refers to that. And how big is this cluster on average? All these things under the null hypothesis. Yeah, you always, so I've repeated it many times already, but you also should repeat that in your head all the time. All these probabilities, expected values that we talk about are under the null hypothesis. Yeah? And then you always have to compare to what you have, and then you can say something if you like classical statistics. And the brain imaging community likes classical statistics, or at least they use them. Whether they like them, that's sometimes not that clear. So these are, this is actually the first bit. So these are what you have already as a handout now. These are what I call the expectations, not too surprising, because these are all expected values. And we need them. Although then in the end, the p-values that you find in the SPM table, they are actually not derived from these expected values, but they are derived from distribution functions which are closely related to these expected values, and in part actually just rely on them. So the second part that we have to talk about in terms of probabilistic properties of excursion set features are distribution functions. And here we will have to talk about the distribution function of the global maximum, which is actually the kind of grandfather of this whole approach. So the distribution function of the global maximum, the distribution function of the number of clusters, where of course knowing the expected number of clusters is of help to actually come up with a distribution function of the number of clusters. And finally, there are numbers missing. The distribution function of the cluster volume, where of course knowing the expected volume of a cluster is helpful. And finally, the maximal cluster volume. There are some numbers missing in my script. So, in case, maybe I should have done that before that, but in case you're currently not clear what the distribution function is. So the distribution function is the function, we've seen that before, that allocates to a random variable the probability that the random variable takes on values smaller or equal to a specific value. So you can also think of this as allocating to each small x the probability measure of the interval from -infinity to small x, or, and this might be more familiar to you, if you think about probability measures that have density functions, then you have, I think, seen cumulative density functions, which are these functions that are on the interval from 0 to 1, and then allocate basically to each x, this we don't need, to each x allocate the probability that the random variable is smaller or equal to x. So they always increase to 1. So if you're at very large values, then the probability that the random variable takes value smaller than that x is usually very large. So think about this in terms of a normal distribution with some mean here, mu, which then is mapped onto this. And if you go out very far here, then the probability that the random variable is somewhere in this direction, so somewhere here, is almost 1. Yeah, so that's the distribution function, and these we will need actually to define these p-values. So that's one step ahead, but it's actually the motivation also to go over all these expectations. Yeah, good. So that's actually now the plan. Questions about the plan? Again, this is all, if you want model formulation, this is all coming up with a very fancy t-distribution to be able to say what you are familiar with in t-distributions all the time, to say if I observe a value here, the probability to observe this or more extreme one is quite small, so I'm surprised, so this is significant. And we are just building this very fancy a null model for statistics that are not as simple as the t-statistic because they extend over space. Yeah? And these statistics are called brain imaging maps, and specifically excursion sets if you threshold them. Good, and we will just we'll just do one by one. So we will start at the beginning of the list and then just walk down the list. Yeah, it's very important that I clean this white space, otherwise I run out of space on my machine. Good. So, first thing, expectations. And And the first expectation we have to deal with and discuss is the expected volume. Now, this always refers to the excursion set. Yeah? So this is the expected volume of an excursion set. So you should always keep in mind that the excursion set depends on U. So this is why I always write it as this E for the set with a little U, because if you change the threshold, if you change the cluster forming threshold, as they say in fMRI, or the level, as they say in this random field theory based p-value correction world, then of course the expectations and the probabilities change. Yeah, I mean, this is fairly straightforward. So if you and we've seen that in examples, if you increase the threshold further and further and further, then at one point you're almost at infinity, and then it's very unlikely that anything, especially under the null hypothesis, is a part, so any part of your domain of the random field is part of the excursion set, or that it's very likely that the excursion set is empty. On the other hand, if you are very low with your threshold, so just do a little drawing again, you're fairly low with your threshold. For example, if you're here, then it's very likely that you have something in your excursion set. If you're here, it's very unlikely. So although it's an expected volume, it's an expectation, it's always dependent on the threshold. Now, what is the expected volume of an excursion set? And this also will serve as a model as we go about these things. We don't do many derivations in this section. We more try to understand the results. Now, the expected volume, first of all, we need to think about what is a measure of volume. And actually here, the measure of volume that is used is Lebesgue measure. So that's why we talked about Lebesgue measure. So this is the volume of an excursion set. An excursion set of level U, and the expectation of it is, of course, the value that we expect to see over many iterations if we perform an average. So think about sampling this random field at a given threshold, and then assessing the excursion set volume. So basically measuring the volume of these two things, and then again doing this for the next realization at the same threshold, and doing this like 1,000 times, then go to the next threshold and do the same thing again. Now, what is the analytical expression for that? That's fairly straightforward. It is given by the volume of the search space. So this refers to this thing here. So that's the search space. In 3D, that's the brain. Times 1 minus the distribution function of the statistic of interest at a level U. So what is this supposed to mean? So think again that this is the probability that if you want x is smaller or equal to U, so x being the random variable that is represented by the random field. For example, if it's a Gaussian random field with variance 1 and expectation 0, then this would be a z variable. This is the probability that a random variable somewhere in this field takes on a value smaller than u. That means 1 minus this is the probability that the random variable takes on a value larger than u. Yeah, so that's now this. And it's multiplied with the volume of the search space. Yeah, so this is really intuitive because it says, okay, the probability that over the field that I'm looking, let's say this is now a 2D field, and I'm looking from it from above. The probability that at any point in this field, the random variable of the random variables that make up this field take on a value larger than u is, for example, 0.5. The volume of this thing is, in this case, it's a rectangle, so the Lebesgue measure is 1 here. The probability is 0.5. Then the expected value of the excursion set at this threshold level is 0.5. Yeah. So that doesn't say how this 0.5 now is distributed. So it's not that this means something like, okay, this half of the space is part of the excursion set. This can of course be of any shape. So let's I hope this is roughly 50%. This, let's say, is at u equals 1. Now, if you go to a higher threshold, then of course the probability that the random variables in this field take on values larger than this larger value of u, so for example 3, is usually smaller. Then effectively the expected volume of the excursion set is also smaller. Yeah. So if, let's say, at this threshold there's only a 20% chance for all these random variables to take on values larger than u, then the expected volume of the excursion set is also smaller and only amounts to 20%. Yeah. Questions about this? Yeah.
So how do we decide the number u? Is it something that is like a convention? We know that value before from the other experiments, or we
the u
set it according to the data by minimizing the number of, I don't know, maybe low maximums?
You mean the u value? Yeah, that's a very good question. There are a couple of things that are worth discussing about this u value, and we'll come back to it. One thing is, as we will see and as we will go on, the whole theory, this whole random field based p-value correction theory only works for high thresholds, actually, meaning where the probability for the random variables to exceed this value r is already quite small. So it has to be chosen quite high. And this was also what the recent debate, at least in 2016, was about, that this kind of theory doesn't work for low thresholds. And then after that, it's actually, so usually the threshold, classifying threshold values is something about, for example, if you have T fields, it's, let's say 2.5 or 3 or something. And after that, it's essentially convention. So you get your p-values for a given threshold, as we will discuss also in the following. But then, of course, the way you set the threshold depends on what you then basically detect. So you also have kind of this false alarm versus miss question. Essentially, there is no right or wrong answer. Everybody should use a threshold value that amounts to 0.001. in SPM, and that is as much as I can say at this point. We will come back to it, but it's an important question, and it's of course determines what you get. But also keep in mind that the numbers that you then get, they of course also change, right? So if you then allocate p-values to clusters, for example, then they will become even more significant if you're at a higher threshold. So going to higher thresholds doesn't punish you in any ways. But we will come back. It will come out for all of them, because everything depends on this u-value. Other questions? No. Now, this so far, this is the distribution function of the statistic of interest, and we will see in a second how this is actually evaluated. What this does not account for at this point is smoothness, but this is just a question of how one expresses there's also something missing. How one expresses in which unit one expresses the volume. So this would be the expected Lebesgue measure, but one can of course also express the whole thing in expected Riesel volume. So maybe let's write it like this. So this should be now expected Riesel volume of the excursion set, and for that. What SPM and the whole, I shouldn't say SPM, the whole random field theory-based p-value correction uses is the third order Riesel volume. So recall that the third order Riesel volume is actually the volume, but smoothness adjusted, and uses the same expression. So the only thing that has been replaced here is Riesel volume by Lebesgue measure. And then already the question of smoothness that we discussed last time comes in. Now this decreases with a larger smoothness. So as I said, I was wrong there last time. So the intuition is the following. Let's say we have a unit Lebesgue measure interval here in 1D. And now we have a threshold u that is, let's say, here. And now we have two random fields with varying smoothness, one being not very smooth and the other one being quite smooth. Both have expectation 0. So the non-smooth thing would essentially look something like this. And a very smooth thing would, that's wrong, it must be centered on 0. Although I could have drawn the 0 a little bit different, so it must be something like this. Yeah, so it has expectation 0, but it's very unsmooth, and something that is very smooth and has expectation 0 would then look something like this. Yeah. So the smoother the thing gets, the lower the expected volume, the expected Riesel volume of the excursion set gets. Yeah. So again, note the difference. So this is just the Lebesgue measure, and no smoothness enters this. So the distribution function of the statistic that we will see how that looks in a second, that is not dependent on smoothness. If you express the expected Riesel volume, then you account for smoothness. Yeah? And for a unit Lebesgue measure volume, it depends on how smooth that is, and the smoother it gets, the smaller the expected value of the Riesel volume. Of course, it still depends on, here on the Lebesgue measure, because as you know, the 3 is the volume but adjusted for smoothness. So if you increase the volume over which you observe the random field, then of course you again increase your expected Riesel value. Yeah. Good. Questions about this? No. So actually that this very nice formula falls out, so where you just multiply the volume of your search space and the probability that any random variable in this random field will take on a value larger than your threshold value. The fact that this falls out depends a little bit on the precise properties of the random field. So it actually requires stationarity, as I then discussed in this little proof there, which is essentially taken straight from the Adler 1981 book. Yeah, I think it's only stationarity that is actually required. Yeah. So you should not take these equalities or these expectations and the stuff that we get, just take them for granted. These are the ones that are being used. But one can, of course, always ask why are they being used, and then you have to dig a little bit deeper and look into how they are mathematically justified. And we will be quite shallow on that. Okay, so that's the expected volume of an excursion set. This is important for computing the p-values in SPM, but it's not directly one of the p-values in the SPM table. It is, however, I think it isn't. I'm not quite sure whether it's in the footer of the SPM table, whether there it tells you what the expected volume is. It's definitely computed when the p-values are evaluated, but it's not one of the p-values itself. It's just used for that, and we will see for what later. Good. Anything about this? No. Good. So now we are getting actually much closer to where the normal world that is not SCAN with me as a teacher is concerned with a random field based p-value correction, because we will finally talk about the Euler characteristic. And whenever you talk to brain imaging people about random field theory based p-value correction, they will be like, Euler characteristic. It is like that, believe me. And we will actually do the same. We will also be like, Euler characteristic. So that's about the expected number of local maxima. And very intuitively, you can think about this as if you want to have more fun following the next stuff, think about the expected number of clusters. Yeah? So if you think from the brain imaging images that you've seen, hopefully by now in some papers, the question is how many blobs are there? Yeah? So I guess you have seen that in fMRI you always get the same activation of the task positive network, whatever task you do, whether you do some decision tasks or you do some social cognition tasks or whatever, you always get the same activation anyway. And the question is how many, under the null hypothesis, how many local maxima, that is clusters, would you get? And then if you observe, for example, 3 clusters, but under the null hypothesis you would only observe, think that at this threshold you would see 1 cluster, then you say, oh, the brain seems to be activated, and it's activated like it always is in every fMRI study since 1995. The local maxima, I will not formally define what a local maximum is. One can do that, but we will not do that here. Think, of course, of local maxima as follows. So if you have something like this, there is one global maximum of this function over space here, which is of course here, so here, but there are also other local maxima which are here and here. Yeah. So these are local maxima. So local maxima are basically defined by the fact that they have take on a value that is larger than the values in their vicinity. Yeah, so that there's basically a neighborhood of points in their domain for which the values that the random variable or the function takes are smaller than the one at the local maximum. You might also already from this appreciate that local maxima and clusters are actually not always the same thing, because if you threshold this, maybe let's see whether I can do that somewhat meaningful. It's a little bit of a mean threshold, but here you would have one cluster, but this cluster has multiple local maxima. And actually you see that in SVM all the time, that you have clusters with multiple local maxima, and then they report the local maxima with a minimum of 8 millimeters apart or something. But if you go to higher thresholds, then actually local maxima and clusters will become the same thing. And we will talk about that when we talk about the number of clusters. So for the moment, you can kind of wishy-washy think about local maxima and clusters as the same thing. We will make it a little bit clearer in a bit. So we are now want to talk about this number mu. So that's an m and that's a u. Again, the expected number of local maxima depends on the cluster defining threshold or the level. And mu is now the number of local maxima. Yeah, that's the number of local maxima of a random field. So that's our random field in d dimensions. Above u, yeah, inside a compact set S, that's fine. If, so that's u, number above u, and because the excursion set is defined as the set in this in the domain of the random field for which the values take on values larger than u, the number of local maxima of the random field above a level u is also the number of the local maxima in the excursion set. This is really trivial, but because we're talking about excursion set features, we can identically talk about the if we have the same threshold value about the number of local maxima in the excursion set versus the number of local maxima of the random field. Now the expected number, and a number means a number, so in the sense like 1, 2, 3, 5, but of course also with decimals allowed, so 1.5 or something. The expected number of local maxima is approximated in RFP by the expected Euler characteristic of the excursion set. So this chi here, that's the Euler characteristic, and the Euler characteristic specifically of the excursion set with threshold u. Yeah. So at this point, the expected number of local maxima, there is no mathematically precise value that can be computed based on the characteristics of the random field, but it's only an approximation. Yeah, so it's approximate, and it's approximated by another expectation, namely the expectation of the Euler characteristic of the excursion set. And after the break, I tell you what the Euler characteristic is. Yeah. So let's have a break until 5 minutes after 9.